In the last lecture, we were discussing the flow past a flat plate at high Peclet number under conditions of forced convection, where the velocity field is specified. Okay, flow So, we had a plate with a heated section, okay, of length L, okay, and upstream of that was an unheated section, okay, and there was fluid flow past this. We assumed that the flow was fully developed, that is, the velocity did not change as a function of the x direction, which is the direction in the streamwise direction. The velocity is only a function of the cross stream direction z, okay, and the Peclet number was large. P e is equal to the characteristic velocity times L by alpha. This was large compared to 1. Okay. So, that was the parameter regime in which we were examining convection. And in this case, the convection diffusion equation is V x partial T by partial x. Okay. I will just work in terms of the scaled temperature. Okay. I will assume the temperature has been scaled. T star is equal to 1 on the heated surface, T star is equal to 0 before the entrance of the heated surface, and T star is equal to 0 far from the surface. Okay. So, basically you have a heated section heating a fluid that is initially at 0 scale temperature, okay, which has come in contact with the surface. And since the velocity was only in the x direction, we had defined the convection diffusion equation partial square T by partial x square plus partial square T by partial z square. Okay. And in this streamwise convection diffusion equation, under the assumption that the thickness of the diffusion of the region in which the temperature of the surface, the heating from the surface affects the temperature field in the fluid. The assumption that the thickness of that region, okay, is small compared to the length of the plate. Okay. We had neglected streamwise diffusion in comparison to cross stream diffusion. Okay. We had neglected streamwise diffusion in comparison to cross stream diffusion, and the convection diffusion equation was V x partial T by partial x is equal to alpha times the second derivative of T with z square. Okay. And very close to the surface, where the thickness of this region where the temperature field is affected by convection and by diffusion from the surface. Okay. This thickness is small compared to L. The characteristic distance for the variation of the velocity field. Okay. The velocity was expressed as a linear function of the distance from the surface. Okay. So, we had used the approximation for the velocity. V x is equal to V s prime times z, okay, where V s prime is equal to dV x by dz at z is equal to 0. The strain rate at the surface. Okay. V s prime is the strain rate at the surface. Okay. And therefore, we got V s prime z partial T by partial x is equal to alpha times partial square T by partial z square. And then came the second assumption, that at a particular location x, okay, the temperature at the location x is not determined by conditions downstream, because conditions downstream cannot affect the temperature at an upstream location. Diffusion is only in the cross stream direction, and convection is only downstream. We have neglected diffusion in the streamwise direction. Therefore, the conditions downstream cannot affect the temperature at a particular location x. Specifically, the total length of the plate cannot affect the temperature at a location x, and therefore, the temperature at that location x has to be only a function of x itself. Okay. So, on that basis we had defined a similarity variable eta is equal to z by delta x, which is a function of x. Delta x is a boundary layer thickness which will go to 0 in the limit as the Peckley number goes to infinity, so that the disturbance due to the surface heating is confined to a thinner and thinner region close to the surface. As the flow velocity or the convection becomes larger and larger, but within this region there will be a balance between convection and diffusion, and this dimensionless parameter etas, that is z scaled by this boundary layer thickness, is order 1, okay, in the limit as the Peckley number becomes large. Okay. So, by substituting this and using differentiation by chain rule, we had got an equation for temperature in terms of eta, if you recall. Okay. The temperature in terms of eta was, okay, minus V s prime delta x square by 2 d delta x by dx. Okay. I am sorry, this alpha here. Okay. dt star by d eta is equal to d square t star by d eta square. Okay. If you recall, we had expressed z and x derivatives in terms of eta derivatives using chain rule for differentiation and using this expression for eta. Okay. Substituted it into this conservation equation, okay, and then simplified, and this is the equation that we got. Okay. The temperature, the boundary conditions for the temperature, if you recall, were T star is equal to 1 at eta is equal to 0. These had to be converted from the boundary conditions for x and z, okay, and T star is equal to 0 for eta going to infinity. Okay. So, those were the boundary conditions. Okay. A similarity solution can be obtained only if this term is a constant, okay, only if this term is a constant, and we had set this term to some constant value. I told you that the temperature in terms of eta will depend obviously on the constant. The temperature in terms of the original variables, okay, x and z, will not depend, and I will show you that. Okay. So, we had used this substitution V s prime delta square by alpha d delta x. Okay, so is equal to some coefficient c delta, okay, and the equation for the temperature becomes, okay, minus c delta dt by d eta. Okay. My apologies, there is, I made a mistake here, it should be eta square. Okay, it should be eta square dt by d eta. You can go back and check that, the calculation in the previous lecture. Okay. And we had integrated this subject to boundary conditions. Okay. If you recall, we had used a substitution, W is equal to dt star by d eta, okay, and therefore the equation becomes dw by d eta is equal to minus c delta eta square w. Okay. You can solve this once to get, okay, w is equal to dt star by d eta is equal to c1, okay, e power minus c delta eta cubed by 3. Okay. Okay, that is the solution. and you integrate once more and you get T star is equal to C2 plus C1 integral 0 to eta d eta prime e power minus C delta eta prime cubed by 3. Okay. So, that is the final solution, and then you have to apply the boundary conditions. T star is equal to 0 as eta goes to infinity, and T star is equal to 1 at eta equals 0. And we had done that in the last lecture and got 1 plus in the numerator is integral 0 to eta. Okay. This is T star of eta. So, that as you recall was the final solution for the temperature, okay, the final solution for the temperature, and it contains within it this particular constant, which is basically an integral from 0 to infinity. Okay. And this integral can be related to what are called gamma functions, okay, and I will briefly define for you what is a gamma function and then tell you how this integral can be related to a gamma function. Okay. The constant in the denominator. Okay. The gamma function is defined as gamma of x, okay, is equal to, okay, integral 0 to infinity, okay, dt times t power x minus 1 e power minus t. Okay. X is the exponent of t multiplied by e power minus t, integrate from 0 to infinity, and you will get this as the gamma function. Okay. You can get a recurrence relation for the gamma function using integration by parts. Okay. So, in this I write, okay, integral of u v, okay, from 0 to infinity is equal to the value of u v at the end points minus integral v du from 0 to infinity. In this I will substitute u is equal to t power x minus 1, okay, and dv is equal to e power minus t dt. Okay. Du will be equal to x minus 1 t power x minus 2, okay, and v is equal to, okay, integral of this, okay, integral of e power minus t is minus e power minus t. Okay. Okay. Substituting that here, I will get this is equal to u times v, which is minus t power x minus 1 e power minus t between 0 and infinity, okay, plus integral 0 to infinity dt, okay, of v times du, okay, du, I am sorry, this is t power x minus 2 dt. Okay. Okay. So, this is x minus 1, okay, t power x minus 2 dt times e power minus t. Okay. And this negative sign is absorbed here in this positive sign, okay, because I should have a negative sign here from this difference, but then I have multiplied that by the negative sign to get this. Okay. The first term t power x minus 1 e power minus t at t is equal to 0, this is 0 if x is greater than 1. As t goes to infinity, this is also 0 because the exponential decreases to 0 as t goes to infinity. Okay. So, this just becomes equal to the second term here, which is x minus 1 integral 0 to infinity dt, okay, t power x minus 2 e power minus t. Okay. And this entire term on the right side is just equal to x minus 1 times gamma of x minus 2. Okay. I am sorry, gamma of x minus 1. Okay. t power x minus 2 is gamma of x minus 1. Okay. So, you can apply this once again. Okay. So, t power x minus 2 is gamma of x minus 1. So, you can apply this once again and you can keep getting higher and higher terms in the series. Okay. So, this is a recurrence relation, okay, for the gamma function. Okay. In particular, okay, gamma of x, okay, x plus 1 is equal to x plus 1, okay, gamma of x, okay, which is equal to x plus 1 x gamma of x minus 1 plus etcetera. Okay. This should be gamma of x minus 2. Okay. Yeah, okay. So, this is the gamma function, okay, and how does this integral here, okay, relate to the gamma function? Okay. You can see that I have an integral here. Okay. How does this integral relate to the gamma function? Okay. So, let me just go through that. Okay. The integral I have here, okay, I is equal to integral 0 to infinity d eta prime e power minus c delta eta prime cubed by 3. Okay. So, that is the integral. Okay. I can define, okay, a new parameter. Okay. I will define a new parameter. Okay. Let us call it as z. Okay. No, z is used in the this thing. So, I will just call it as w, okay, is equal to c delta eta prime cubed by 3. Okay. This implies that dw is equal to c delta eta prime square. Okay. And eta prime in terms of w is that eta prime is equal to 3w by c delta whole power 1/3. Okay. So, this will be equal to c delta into 3w by c delta whole power 2 by 3, okay, which is equal to c delta power 1/3 into 3w power 2 by 3. Which is equal to c delta power 1/3 into 3w whole power 2 by 3 into d eta prime. Okay. So, what this implies is that d eta is equal to dw by c delta power 1/3, okay, 3w whole power 2 by 3. So, therefore, this integral I can be expressed as integral 0 to infinity, okay, okay, into dw by c delta power 1/3, okay, 3 power 2 by 3, okay, into w power 2/3 into e power minus w. Okay. Okay, because c delta times eta prime cubed by 3 is w. Okay, so, I just get exponential of minus w. Now, I have w power minus 2/3 e power minus w dw integral from 0 to infinity. Integral of w power x minus 1 dw is going to be gamma of x. Integral of w power minus 2/3 integral is going to be gamma of 1/3. Okay. So, this is equal to gamma of 1/3, okay, by c delta power 1/3, okay, times 3 power 2 by 3. Okay. So, this is the integral that we had started off with. Okay. This is the integral that we had started off with, which was in the denominator here, okay, which was in the denominator of this expression, okay, which is in the denominator of this expression. And therefore, the expression for the temperature T star is equal to 1 minus, okay, C delta power 1/3 3 power 2 by 3. Note that that integral was in the denominator, so I have to take the inverse of I by gamma of 1/3 integral 0 to infinity, 0 to eta d eta prime e power minus C delta eta prime cubed by 3. Or if I write it back in terms of the original variable, okay. So, if I write it back in terms of the original variable, I will get 1 minus C delta power 1/3 3 power 2/3 by gamma of 1/3, okay, integral 0 to z by delta x of x, okay, eta z by delta x, okay, of d eta prime e power minus C delta eta prime cubed by 3. Okay, so, that is the temperature field. Okay. And what is the heat flux at the surface? The heat flux at the surface is going to be Qz is equal to minus k partial T by partial z. I can express this in terms of T star, the scale temperature, minus k into T naught minus T infinity. Okay, so, let me check the symbol I have used. Yeah, I have used Tw as the wall temperature. Okay, so the scale temperature is in terms of is defined in terms of Tw here. Okay, so the scale temperature was defined in terms of Tw minus T infinity. Okay, so let me use that same expression for the scale temperature. Okay. By delta x, okay, d T star by d eta. Okay. This is the surface flux at eta is equal to 0, because z is equal to 0 is the surface. Okay. And this is equal to minus k into Tw minus T infinity by delta x into the derivative of the temperature with respect to eta. Okay. So, this is the temperature as a function of eta, okay, and I have to take the derivative of that. The derivative of an integral is the value at the upper limit of integration. Okay. So, this is equal to C delta power 1/3 3 power 2 by 3 by gamma of 1/3, okay, into e power minus C delta eta cubed by 3, okay, at eta is equal to 0. Okay. And at eta is equal to 0, this term just becomes equal to 1. Okay. I should note that I have a negative sign here. Okay. So, I should have a negative sign here also. Okay. Negative and negative will be give me positive, and I just get k into Tw by delta x into C delta power 1/3 3 power 2 by 3 by gamma of 1 by 3. So, that is the expression for the heat flux at the surface, and before that I had got the expression for the temperature. How do I find out this delta, okay, this thickness delta? Okay. So, I have to go back to the differential equation for delta, okay, which was this one. Okay. This was the differential equation for delta. Okay. So, I have to get the expression for delta from that. Okay. Recall that the differential equation for delta was that Vs prime delta x square by alpha d delta x by dx is equal to C delta. Okay. So, that was the differential equation for delta. Okay. The boundary layer thickness. Okay. So, I can re-express this as 1 by 3 Vs prime by alpha d delta x cubed by dx is equal to C delta. Okay. Integrate this one time, okay, and you will get delta x cubed is equal to 3 C delta, okay, x by into alpha by Vs prime, okay, plus some constant of integration d. Okay. This is the expression for delta cubed. Okay. And at x is equal to 0 is the start of the heating section. X is equal to 0 is the start of the heating section, and at that location there has been no heating yet. That means that the boundary layer thickness has to be equal to 0 at x is equal to 0, okay, or delta x has to be 0 at x is equal to 0. This implies that the constant d is equal to 0, okay, and therefore, I get an expression for delta x. Delta x is equal to 3 C delta x alpha by Vs prime whole power 1/3. That is the equation for the boundary layer thickness. And I can substitute that into the correlation for Qz here at the surface, okay, at z is equal to 0. Okay. Qz at z is equal to 0 is equal to k into Tw minus T infinity by delta x, which is, okay, 3 C delta x alpha by Vs prime whole power 1/3, okay, into C delta into 3 power 2 by 3 by gamma of 1 by 3. Okay. Okay. That was the expression that we had. I just substituted the value of C delta in here, okay, in this expression to get the expression for the flux at the surface. And you can see that C delta cancels out over here and over here, okay, and therefore, you get something that is independent of C delta. As I told you earlier, the expression in terms of the similarity variable eta will depend upon C delta, the constant that we have assumed. The final expression for physical quantities like the temperature and the flux will not in general depend upon C delta. Okay. And cancelling these out, I get k into Tw minus T infinity into 3 power 2 by 3 by gamma of 1/3, okay, into Vs prime. Okay. This 3 power 1/3 and 3 power 2/3 can be cancelled out. So, I will just get 3 power 1/3 here, okay, Vs prime by alpha x whole power 1 by 3. Okay. Note that the boundary layer thickness increases as x power 1/3. Okay. The boundary layer thickness in this case increases as x power 1/3. The flux decreases as 1 over x power 1/3 with downstream distance, okay, from this calculation. Okay. This is the local flux. We have to calculate the average flux and the correlation for the flux. That we will continue in the next lecture. I will see you then.